Hey guys, welcome back. So what we're looking at here is going to be our goal over the next several tutorials to build up to. So it's a particle GPU extension that's driven by terrain maps that are generated in several different ways. What we're going to be looking at in this tutorial is one way to generate one of those terrain maps. In subsequent tutorials, we'll look at a couple other ways to generate terrain maps. We'll look at how to build interactivity. We will look at how to generate a variety of different effects using the terrain maps. For example, what we're seeing on the screen at the moment. And then finally, we'll look at a couple of different ways of rendering and visualizing things nicely. So that gives you a sense of where we're going. It is going to take several tutorials to get there, so I hope everybody can bear with me. I think it'll be a fun and worthwhile journey. So with that, let's jump into things. So today specifically, what we're going to be doing is learning how to generate a custom terrain fractal using GLSL, and then from there using that generated fractal to calculate a gradient that can be used as an input to really anything, this being just a single example. So this is an example of what we're building up to today specifically. So as we can see, it's a height map. It looks a lot like a mountain range. We're going to parameterize things to make this pretty configurable, and we will understand kind of the at least high-level math underlying the algorithm. So let's jump into things. Now, I guess before we get started, let's build a very simple visualization to let us actually understand what we're looking at. So I'll drop down a grid. I'm going to make it mesh. We'll say rows 500 by 500. I'm going to drop down an attribute create, compute normals, compute tangents, Alt N for null, I'll middle mouse, create a geo. And then we'll do a camera, a light, a render, a null, and then last we'll need a Fong. All right, and then finally we'll just need some maps for our Fong. So we'll make this a null. We'll grab a normal to get a normal. We'll grab a slope. That'll give us the gradient. We'll make that 0 and strength of about 100. And what else do we need? Just a color. So I will just use, actually, I'll just use a null for the color. Cool. Oh, and I guess we also will need a height map. So maybe I can use, so another null, height map. We'll use this for the color, and then this can be the normal. Cool. And then we'll just add these maps. Our color map, our normal map, and then we'll enable height map. Our height map, just place vertices. And all right, we're starting to get there. 2048 by 2048. I like to render with 16-bit float. Let's tilt and zoom. Okay, make this noise a little bit higher resolution. Make sure it's 32-bit float. And okay, so now we have a little bit of a visualizer. I don't think I like that color, so I'll just bypass the slope and just use the grayscale value for color. And then what else do we need? We probably want to displace a little bit less than this, maybe something like 0.15 will be good. And okay, so now I'm going to try and just zoom in a little bit. All right, that looks pretty good. You could obviously do stuff like post, depth, blur, for example, just a really quick one. I'm not going to go further into anything post besides this, but since I'm here already, why not? And then we'll rearrange from camera space. I don't know, probably something like 5. And yeah, okay, cool. So now we can use a blur, and we can just blur the white values just ever so slightly to give us a little bit of depth perspective. And then I like to drop a blur in right before that as well, because our depth texture is not our depth map is not anti-aliased. So a little bit of blurring helps things out. So there's a lot more you can do here. PBRs, custom shaders, yada, yada, yada. I'll probably get into some of those in later tutorials, but not for today. So for today, we have a height map visualization, and that will be good enough for us. So what I'm going to do now is get this up to 1,000, and then collapse all these guys. Cool. So let's translate this to get a little bit of motion. Cool. Now, around now, you may be wondering, what's the point in a custom terrain procedural algorithm when we can just drop down a noise and use that? I mean, after all, it's what I'm doing right now. So to answer that question, I think it's helpful to look at a few examples of noise. Sorry, not a few examples of noise, a few examples of terrain, which we can view alongside our noise. So one of the things that we'll notice is this prevalence of ridges, right? Pretty obvious. Mountain ranges have ridge lines. Those ridge lines are very sharp. One thing that we will see is demonstrably missing in our unadjusted noise is this concept of ridges, especially ridges that occur kind of along these lines, right? We can see a line running. Our human eyes are pretty good at picking those out. Complete absence of that in the normal, just simplex noise. A couple other things. Real terrain is going to have flat parts at lower elevations. It's going to have a gradual slope up to much sharper parts at higher elevations. And then what we can see in this image and this image is that for areas in high elevation, right, like both of these are taken at near the tops of mountain ranges, it seems, the local minima are still going to be much flatter and smoother than the surrounding areas. So even if the absolute elevation is pretty high, we have to take a relative elevation and relative slope into account, because as things erode, naturally the sediment is going to fill up the local minima. So we need to be cognizant of that regardless of how high up on an absolute basis our point is. And then finally, we want to have some semblance of pattern formation without too much regularity. And last but not least, here's a good example. We want to have this self-similarity, i.e. fractals. So noise, just kind of without any adjustments, is going to get some of the way there. We can see there's some pattern formation. There's not a ton of regularity. There is definitely self-similarity, but we're missing some points too, right? There's no differentiation between the different areas of the map and how sharp things are. So it's just homogeneously kind of the same fractal degree across the entire height map. So that's a problem because one of the things that we highlighted is exactly that the sharpness needs to vary with altitude, both locally and absolutely. And so that variance is going to take the form of having a different fractal parameter for different parts of the height map. So in the valleys, we're going to accumulate much slower. And by accumulate, I mean add additional height to our terrain map. We're going to accumulate much slower for those areas. So they're going to have a smaller fractal dimension than areas that are higher up on the height map. They're going to have a higher fractal dimension, meaning a greater contribution from each additional octave to the final value of the noise function. So hopefully that gives a little bit of insight into why regular noise isn't quite good enough. Now you might say, sure, but you just dropped down a regular noise, didn't make any adjustments. Potentially fair. Let's see if we can adjust this a little bit and make things look a little bit nicer. Let's increase our period, maybe give us a lot more harmonic, something like 7, maybe a greater amplitude, higher offset, maybe a bit more of an exponent. So, all right, now we're maybe getting there, right? Things are looking a little bit more terrain-like. Certainly an improvement over just the unchanged noise. Still, though, we can see that it's not quite getting there. For example, we're not seeing this multi-scale variation at all. Even in the areas where the altitude is low, the sharpness is still exactly the same. And while we have some of these isolated peaks, there's nothing like a clear valley or ridgeline in play. So we're not getting kind of this dynamic where you can use your eye to trace the line of mountains. This is more like spots of mountains, which does happen sometimes, but is not the general phenomena that we're trying to simulate here. So even when we kind of dial in noise to get as close as possible to what we're looking for, without some additional modifications, it's just not really going to get the whole way there. So what we're going to do is build our own noise generator using some GLSL code, and we're going to essentially recreate a fractal noise algorithm, just kind of using the general fractional Brownian motion framework. And we're going to tweak a few different things to get to the type of output that we're looking for, i.e. one that has a heterogeneous fractal dimension, is able to have higher degrees of sharpness and detail for higher altitudes, and one that can propagate the effects of erosion, i.e. smoothness, across valleys at any level of elevation. So, to maybe just give a little bit of written example what I'm talking about, also just trying to find more uses for this writing pad. Kind of drawing out the distillation of what we were talking about there. So we have a mountain range. We want to make sure that it is jagged on top So, kind of up here, we want to make sure there's jagged parts. We want to make sure that at any local minimum or any global minimum, which is going to be defined locally by slope and absolutely by elevation. We're going to make sure that both of those areas have a low h, which is going to be defined as our fractal dimension. And then our jagged areas are going to have a high h for the jagged areas. So again, what that means is that for each octave, we're going to be adding more to our final function value for jagged areas and less for areas in the valleys. We're going to make sure that the sharpness then is proportional to the local altitude, or really can say the local slope. And we're going to make sure the sharpness is proportional to the absolute altitude, the elevation, like I said, over here. And then finally, patterns without too much regularity and with a ridge line. So that's really just a quick illustration to kind of try and codify what we're going to be looking for here. And then the last thing I want to say before we jump into actually building this algorithm is that this is where I got the actual logic from. Texturing and Modeling, third edition, by this collection of authors whose names everyone probably recognizes at least a few of. Worley, Perlin, Peachy, all pretty famous in the noise world. Musgrave, less famous, but no less impactful. And he's actually the one who developed the specific hybrid terrain fractal that we're going to be working with today, which enables us to have heterogeneous fractal dimensions that will give rise to a lot of these dynamics that we're seeking as far as the aspects of the terrain. So I'll drop a link to that in the description. The last thing, highly recommend we buy used. All right, so back in our tutorial, what are we going to do and how are we going to create our noise? We're going to create our noise using a GLS LTOP. And so first we'll just drop one down. And I'm actually going to create a parameterized component even before we get started. So I know that I'm going to need a lot of parameters, so I'm just going to add those before we get going. So I'll need octaves, make that 10, and I'm going to default it to 10. I want a float for amplitude, default to 1, range 0 to 2. We'll want a period, again, default to 1. We will want a gain, default to 2, range 1 to 3, default 2. Range 1 to 3. Cool. Just going to copy and paste that and turn this into lacunarity. H, which is going to be our fractal dimension, that we're going to default to 1, and it'll go from 0 to 2. Fractal dimension. What else are we going to need? We're going to need a translate. That's going to be a vec3. we'll need an offset. That's going to be a float. Add that default to 1. And then what else will we need? No, I think that'll be it. Or at least enough for now, and we can add more if we need to. So then I'll just open up these parameters and jump in here. I'm going to set up some vectors. So here, just a vector for each. Oops, U offset H linearity octaves amplitude and period, and then we'll just associate all of these guys. All right, so now we got some values to work with. And now we can start actually editing the shader. And then I guess the last thing I'll do before we do that, get an out. And pipe that into here. Cool. So now we can see what's going on as we are developing. Cool. All right, so let's jump in. And I'll get this all set up. Hopefully that's pretty visible. We'll want to see that, and then we'll come back up here. Cool, and that should give us some good stuff to work with. And then maybe I'll just see if I can move this down just a little bit. Nice, okay, cool. So, all right, let's first build up to this. We're going to, let's think. Okay, so first we need a noise. Essentially what we're going to do here is going to be creating a noise. We're going to sample the noise. We're going to create a fractal for loop that's going to sample that noise, incrementally accumulate it with weights that vary based on condition, as well as prior values. So first we need a noise that we can sample. You can do a few different things to get that. You could drop a noise down and pipe it in. I don't like that because if you try to sample a location that's outside of 0 to 1 on the UV space, you get an undefined error, and then you're left with basically just different extend methods, which generally result in just output that I find unattractive if you try and do anything remotely interesting with it. So we're left with noises that we are generating implicitly via functions within our code. TouchDesigner provides a pretty handy inbuilt way to do that. So let's take a look. TDSimplexNoise is the function. And so by calling that and just passing through a vec3, or it can be a vec2, we can just easily get a implicitly defined simplex noise function. And if we do something like this, 3p equals to increase our period and transform that. And then what we'll do is also make the alpha 1. Key. Cool. So nice. So now we can see that our period is a little bit higher, meaning we can see more of the detail that's going on here. And we can see that SimplexNoise is working. So I will go through this first, just using this TouchDesigner SimplexNoise for ease. But I will, at the end, note a way for optimizing that. So without further ado, let's build our terrain. So first things first, let's get our uniforms. So we need a gain. We need a offset. Linearity. H. We need an int. Octaves. Amp. Period. And a vec3 for translate. All right, so that should be most of them. They're all associated. And let's just make sure it all works by doing this. All right, so it looks like things are working. That's great. Vec3. Cool. So now let's start to build our terrain algorithm. So first, we're going to define a new variable that's going to be our transformed point. So we're going to multiply it, scale it by our period, and then add the translate. Function does not return a value. That's fine for now. We'll just do that. Let's say float t equals terrain of p. And we don't need that anymore because we're scaling it within the function. And then we can just say t. And then maybe what we can do is say float results TDSimplexNoise points, and then we'll return that result. All right, cool. So now we're back, and we have a terrain function that's returning a value that we're using in our heightmap. And it'll just give us a little bit of translation. Cool. All right, so now we have to build our actual algorithm. So first we need to sample a heightmap. And that is actually going to be what our SimplexNoise function call does. So we'll say noise equals TDSimplexNoise point. We'll say signal equals noise. And then we want our result down here well, we'll get to that, I guess. So I'm going to leave it for now. I've returned the signal. And okay, so then we want our signal to be U offset minus signal. And the reason for that is because our height map, as most height maps should be, we want it to be in the positive space. This is generally stylistic, but I do find it returns better results. So I'm going to leave it in. One optional thing you can do here, well, is get the absolute value of the signal and just take positive only values. This will ridge the base map at 0, since simplex noise is generally on the range -5 to 5. This is pretty stylistic, so I'm going to leave it out for now. But you can see even here when I'm commenting out, we see the ridges, or sorry, when I leave it in, we see the ridges forming, which is exactly what we're looking for per our image investigation earlier. And then we're going to square the signal to just emphasize the features of the terrain a little bit more. Cool. So now, oops, I guess this should be up here. Now what we're going to do is initialize loop variables. So here we want our result to be initialized equal to the signal. I'm going to get rid of this up here. We want a weight to be 1. We want a frequency that we're starting out with to be 1 as well. And that's going to be it for now. So then we just have to create our for loop. And I equals 0. I less than u octaves. Be thankful the TouchDesigner supports the use of uniforms and non-constants in our loop declaration. It makes our lives a lot easier. All right, so now inside of our loop, we are going to say a scalar point by our lacunarity. We are then going to set our weight equal to the signal times our gain parameter. So what this is doing is scaling octave weight by signal at this location. And if you remember, our signal at this point is a function of the height. So proportional to altitude. So this is one of the terms that's actually getting to some of the overarching design features that we're looking to have with this algorithm. We're going to clamp our weight. 1. Oops, nope. Weight 0, 1. Clamp it. Then we're going to resample our noise with our new point that is now being updated with our lacunarity here. Take the absolute value again. Now we're going to scale our signal by our weight. And what this does is scales signal proportional to height, because weight is itself already proportional to the height. Then we're going to accumulate. And we are going to accumulate. I'm going to start returning my result now to get rid of this noise. And then we need to make sure that we're updating our frequency each pass by multiplying it by the lacunarity. And then the last point is that we want to make sure that we are accumulating proportional to the frequency and the fractal dimension. So finally, scale this by the amplitude and make this 32-bit float and 1024 by 1024. Actually, probably want resolution as a parameter. But I definitely want it to be 32-bit float. Whoa. Now what's going on here? So we get our period down, more octaves, less gain. All right, and what we can see is that our that should be higher. Oops. There we go. We can see that we're starting to develop an actual height map that's starting to resemble the real terrain that we were looking at. So we can see, one, obviously there's much more variation across scale. So we have our peaks that are much sharper than the corresponding valleys. And we can also see that there's, for example, if I pause it, areas like this that are higher absolute altitude that are smoother. So we do have a lot of that appearing as we wanted, in addition to stuff like ridge lines. So from here, there's really just a lot of tweaking to find the part of the parameter space that you like the most. So feel free to play around with all of these different parameters and really dial in what you are looking for in a terrain. One thing that should be a negative, which will really calm things down. And then I think we should be able to go back to our original values. Okay, nice. Yeah, so make sure that's a negative so that we are scaling the signal down with increasing frequency and not making it louder. That was resulting in a lot of the noise you were seeing just a moment before. So with that negative H, yeah, now we can see that we have a pretty nice looking procedurally generated terrain here. Can increase the amplitude, and then you can use things like offset to determine, I like to think of it as kind of what the base elevation is going to be, and then use some of the other parameters like amplitude to dial things in and tweak it a little bit. Higher fractal dimension is going to be smoother. Lower is going to have more sharp ridges. Amplitude, pretty self-explanatory, and then gain is going to result in the level of detail that you're seeing kind of on the mountainsides, if you will. It's not terribly evident right now, but I guess if we look at colors, that doesn't give you a ton either, but it is more apparent depending on how you use this output. So worth playing around with, but I found that a gain of 2, an H of 1, and a lacunarity of 2 are pretty good places to start. An amplitude of 1 and a period of 1 don't really hurt either. So yeah, that is basically all you need to create a procedurally generated terrain fractal. I use this a lot across quite a variety of different projects, many different use cases. One thing that I will part with is that apart from just using this as a height map and visualizing it the way that we're visualizing it here, one, if you're doing this, you could easily incorporate things like a dynamic coloring based off of the height. You could calculate your normals on the fly and use those for better shading. There's really no limit to what you could do just from this implementation alone. But what I will often do is add a slope, set the 0 point to 0 and strength to something like 100, and then if this is vertical and this is neutral, vertical, then what we also have is a nice anti-aliased gradient field that we can use for a lot of stuff. So just as an example, if I use a fluid simulation and decide that I want to hook this up as the what do you call it, velocity field, then if I pipe this in here and here, then we can see, oh, potentially biting off more than I can chew here at the end. Mix. This is so just a real quick utility to give myself a little tool to play with. There's a lot of this going on. I'll tune this down a lot. And okay, so this is generally acting a little bit funky, but you can start to see that it is you start to see that it is quite an extensible framework, and it can lead to some pretty interesting results. So I also just like it because it allows you to use noises that are just a little bit more interesting and off the beaten path than the just noise tops that everybody drops down to start using. So I think that working this in to your general workflow just as another noise generator can be a way to add some interest and start to develop a style that's a little bit unique to yourself. So I guess in closing, I hope this was helpful to everyone. I hope that procedural generation of terrain height maps make a little bit more sense now. And just to close, a reminder that this is what we're building up to. This being a practical example of using that terrain height map gradient. So as a sneak peek, jump in here and can see that right here, we're using this gradient, which is very similar to what we were just looking at, using this procedural height map. So, like I said, that's one example of how this can fit into a bigger project. We're going to touch on a lot of the other parts of that bigger project and how to put it all together over the subsequent several tutorials. So I hope you guys all enjoyed this, and the project files and source code are going to be available on Patreon. I will drop the links for the textbook reference in the description. And I hope you guys have a great day. I'll talk to you soon.